We are on topic 6, function analysis and miscellaneous. And I've recently renamed it to function analysis and miscellaneous. Out of our 10, we're on number 5. I'm sorry, we're on number 6. Topic 6. All right. The most recent exams, you see, this is on there. This has been on there quite a bit within the last 5 years. Before then, not so much, but for the last 5 years, it's been really consistent. Usually no calculator, though some of them do. Okay, the function analysis questions are no calculator. The miscellaneous can definitely have a calculator on it. So we are going to start by taking a look at, let's just take a look at the question from 2018 that falls into this category. This would be more of a miscellaneous type of question, not a function analysis question. This one was with a calculator. It was number 2. And this is the question that the kids came back complaining about after the test. The plankton problem, we fondly refer to it now. Researchers on a boat are investigating plankton cells in the sea. At a depth of h meters, the density of plankton cells in millions of cells per cubic meter, it's our units, is modeled by this equation. So P is density. So P has these units, all right? H is the depth. So P is good for H from 0 to 30. The density is modeled by F of H for H greater than 30. Okay, we don't know what F is. Part A, find P prime at 25 and then interpret the meaning. So P prime at 25 will be, all right, let's put this into our calculator because I'm sure we're going to need it again. So carefully put this into our calculator where X is H, and I'm double checking to make sure that I have it in there right. I think I do. And then, oops, gosh darn it, negative 0.0025 h squared. Okay, there we go. So home screen, I want P prime, so math 8 with respect to X of my Y1 at 25, and I get that number. So that's my P prime at 25. I don't have to give units for it, but I will have to use correct units in my interpretation. So what does P prime mean? Well, P prime is a rate. So it's the rate of change of P at 25 when H is 25. So when H equals 25 meters, remember we always have to give units for our time or our whatever our independent variable is. I'm describing what P is. The density of plankton cells is changing at a rate of P prime at 25, and now I need the units for the P prime of 25. So the units for P prime would be, remember P prime, just think to yourself, P prime is dP dH, right? So units of P divided by units of H. Well, units of P are right here. Units of H are meters. So millions of cells per cubic meter, that would be units of P, and then per meter for units of H. Or you could say millions of cells per meters to the 4th power. That's fine as well. This was worth 2 points. 1 point for our answer, 1 point for the meaning with units. So remember, independent variable with units, description, and then finish with units. Always, always, always. 2 sets of units. All right, part B. Consider a vertical column of water in the sea with horizontal cross sections of constant area 3 square meters. Okay, so I'm visualizing, when I read that, I'm thinking of a vertical column of water, so my head kind of goes to like a cylindrical column, and that does have a constant, each cross section will have a constant area in this. So this is a good visual. Maybe it's not a cylinder, but each cross section is exactly 3 square meters, so this is a good thing to consider. Okay, so here would be a depth of 0 meters. Here would be my depth of 30 meters, because I see we're going to 30 meters. Okay, to the nearest million, how many plankton cells are in this column from 0 to 30 meters? Okay, I know that each cross section is 3. So each cross section has an area of 3 meters squared. The area is 3 meters squared. So in my mind, I'm going to an integral because I know that there's plankton cells. In every cross section, we have plankton cells, right? So if I start at 0, get those plankton cells, add up the next slice, and the next slice, and the next slice, and the next slice, go all the way to 30. I should have all of the plankton cells then, right? So I'm thinking of an integral. Integral from 0 to 30 of what? Of what? Well, I have my density times my area. In my mind, that's going to work. So I'm going to write the area is 3 square meters times my density, which from 0 to 30 I need to use P, not F, I need to use P. So this would be P of H. So in my mind that's going to work. Now let's do a little unit analysis to confirm that that's going to work. When in doubt, I go and do a little unit analysis. So I am adding up, this is just adding, right? 3, the units for the 3 are in square meters. The units for P are in millions of cells per cubic meter. That's what they told me up here. Millions of cells per cubic meter. Now don't forget your units for H. Units of H are in meters. Does that give me plankton cells? It sure does, because these units cancel out and I'm left with millions of plankton cells. So yes, my little unit analysis confirms what makes sense to me. The rest of it is just a calculator situation. So we've got Math 9, 0 to 30. 3 times what I have stored in for my, oh gosh, hang on, what I have stored in for my Y1. Let me go insert this. Y1. Okay, so I get that. So they tell us they want it to the nearest million. So to the nearest million, I think I would probably write this. To the nearest million, I'm going to round that to 1.675 million cells. Okay. This was worth 2 points. 1 point for the integrand. 1 point for the answer. Part C. There is a function u such that f, okay, what was f? F was the other way that we could write, it was the density of the plankton cells for H deeper than 30 meters. So that F is between 0 and U, some other function, for all H deeper than 30 meters, so greater than 30 meters. And they give us this integral. So integral 30 to infinity of U dH is 105. The column of water in part B is now K meters deep. It was 30 meters deep, now it's K meters deep, where K is bigger than 30. So in my mind, I'm going to take that same column of water and I'm going to make it longer. So we were going from 0 to 30, and now we're going from 0 to K. All right? Very good. K is bigger than 30. Write an expression involving one or more integrals that gives the number of plankton cells in millions in this entire column. Well, up here we found the plankton cells from 0 to 30. We just need to do it for an extension here. So this is going to be what I found in part B plus the next part. So the next part will be from 30 to K of 3 times the density here. Now I can't use P because P is only valid for 0 to 30. I need to use F because F is valid from 30 to K. So F of H dH. So I have done their first thing. I've done what they asked first. Write an expression involving one or more integrals that gives the number of plankton cells in the entire column. Now we want to explain why the number of plankton cells in this column is less than or equal to 2,000 million cells. So now I know I'm going to be using this information here. Okay? This is just a number. I found that number up here. So I'm not worried about that at all. This is something different though, right? So I'm going to say that, all right, this is equal to what I found up here, 1675. I think I'm probably going to give the 3 decimal places there. I think we would be fine if we rounded it, if we gave that same answer, but I'm just going to give that number. I'm going to take the 3 out because there's no 3 up here in this integral, and I'm going to have to compare. It makes sense to me if I take this 3 out, then I have this integral. Let me explain this. Took that 3 out. This integral, since f is less than u, then this integral must be less than this integral. It makes sense to me, right? So I'm going to say this has to be less than or equal to that same value plus 3 times the integral 0 to infinity of u of h dh. It must be, since f is between 0 and u. So that must be true. I could actually keep the k here, and that would be really obvious. And now I would say, now I'm going to substitute in that infinity. Okay, since we're given k, and they're saying that k is a number. It's a number of meters deep, so it is a number. So that's true. Okay. And now this is equal to 3 times 105. And is that less than 2,000? Let's find out. There's that number, plus 3 times 105, and that is indeed less than 2,000 million. Okay? In millions of cells. So, a little confusing, a little bit. This was worth 3 points. The first point was for the integral expression. The next point was for comparing, what they say compares improper integral. So I think that's where we did our inequality and we got our improper integral involved, the 105. And then the third point was for the explanation, which was our entire response. Part D. A boat is moving on the surface of the sea, and at time t greater than or equal to 0, the position is x of t, y of t. So all of a sudden I see that I'm in a parametric equation problem. X prime is this, y prime is that. Time is measured in hours. Okay, find the total distance traveled. That's just a formula. All of a sudden, this part is going to be easy if you know that formula. Total distance traveled from 0 to 1. So I know my total distance traveled formula is just the integral 0 to 1 of my speed, square root for speed. X prime squared plus y prime squared dt. This ended up being a really easy part. Sometimes part D is easy. Okay, so math 9, 0 to 1, square root. I need to square x prime, so I'm going to carefully do that. Sine of 5t, close the parentheses on x prime, and then square that, plus my y prime, close the parentheses on that, square it with respect to x. Practice, practice, practice putting things in your calculator, you guys. We get 757.456. They didn't ask for units, so I'm not going to give them. This was worth 2 points. 1 point for the integrand. 1 point for the answer, the total distance. Okay, this was a rather long problem. Okay, when did we use our calculator? We did use it quite a bit. The only part that we didn't use it was part C this time. Okay. All right, next up, I think we're going to go and do the problem from 2017. This is more of a function analysis question. So let me go find that so I can tell you what. Okay, 2017, number 5, no calculator. Function analysis problem. So in this problem, they give us f. They just give us an f. All right. Part A, find the slope of the line tangent to the graph of f at x equals 3. This isn't bad. Slope of the line tangent, we've been doing that since unit 1. That's just the derivative, right? So for the derivative, you can either use the quotient rule here, or you can bring the denominator to the top and give it an exponent of a -1 and use the chain rule. Quotient rule or chain rule, those are your options. And I always, in my mind, I bring it up to the top and use a -1 exponent. I don't write it down, but that's what I'm doing. But for you guys, I am going to write it down. So I am bringing the denominator to the top and giving it an exponent of -1. And now I'm using the chain rule for the derivative. So -1 times 3, reduce your power by 1, and then multiply by the derivative of the inside. So 4x minus 7. Okay, that's fine to leave it like that and plug in x is 3 right here. That would be perfectly fine. Or we can go ahead and move this to the denominator. probably, if I was just writing the test, I would just right now put in 3 for x. I know I would. But I know that some of you would use the quotient rule, and I want to get to where you would get when you use the quotient rule. So this would be negative 3 times 4x minus 7 on top, and in the bottom we'll have that squared. Okay? So if you use the quotient rule, remember that the derivative of 3 is 0, so your very first term in the quotient rule is going to be a 0. 0 minus 3 times the derivative of the bottom over the bottom squared. So that's fine. And now we are going to plug in 3 for x. So f prime at 3 will be negative 3 times 12 minus 7 over 2 times 9 minus 7 times 3 plus 5 squared. Safe stop. Slope of the line tangent at x equals 3. This was worth just 2 points for f prime of 3. So I'm guessing that they split that up into having the correct derivative and then for the answer, but they didn't say that, so I'm not sure if they split it up or not. Just a guess. Part B. Find the x-coordinate of each critical point of f in this interval, and then classify each critical point as the location of a relative min, max, or neither, and we have to justify. So first of all, I'm going to say what a critical point is. Sometimes that's worth a point. So I'm going to say f has a critical point when f prime equals 0 or f prime is undefined. Okay? F prime is 0 or f prime is undefined. So, I'm going to find those two out. So let's see. F prime, which is what we just found here, well, this is equal to 0 when the numerator is equal to 0, right? So when 4x minus 7 equals 0, so x is equal to 7/4. So that's a critical point. But we also need to consider that since it has a denominator, the denominator could be 0, making f prime undefined, right? So f prime is undefined when 2x squared minus 7x plus 5 is 0, right? So let's factor this if we can. 2x and x, 5 and 1, minus and minus. Does that work? It does. That factors that way. So x will be 5/2 and 1, but both of those are just outside of the interval that they gave us, right? So when we, so our only critical, so I will say f has a critical point when x is 7/4 in the interval 1 to 2.5. Now we have to classify that as a relative, the location of a relative min, max, or neither, right? Since we have all this information about f prime, I'm going to do the first derivative test. So we're only considering what is happening. I'm going to do a sign chart on f prime, okay? And I'm going to bound it by 1 and 2.5 or 5/2. So to the left of 7/4, maybe at just slightly over 1. At slightly over 1, this parentheses will be negative. Negative times a negative is a positive. The denominator is positive. So this is positive. Since the denominator is squared, I know it's going to be positive. Just to the right of 7/4, maybe at 2, if I put 2 in for x, I'll get a positive times a negative divided by a positive. So that is a negative. So I will say f has a relative max when x is 7/4, since f prime changes from positive to negative there. And I apologize for the lack of space there, but know that on the actual exam you're going to have a ton of space. So you won't have to cram in anything unless you write super, super large, which none of you guys do. All right, part C. Using the identity that this function, which was our f, that's our f function, f is equal to this, evaluate this improper integral or show that the integral diverges. So what they did here was they did a partial fraction decomposition for us. We don't have to go do it ourselves. That was awfully kind of them. So the integral from 5 to infinity of f of x dx is equal to the integral 5 to infinity of our partial fraction decomposition, which they very kindly did for us, dx. Okay, time for antiderivatives. Now, my top boundary is infinity, so I know I cannot put a boundary of infinity. Not only that, I know they're going to give me a point if I write this answer as a limit. So I'm going to write this as my top boundary is going to infinity. And now I'm going to write my antiderivatives. So the numerator is 2, so I'm writing that down. Now for this is going to be a natural log since the derivative of the denominator is a number. The derivative of the denominator is 2, right? So it is going to be a natural log of the absolute value of 2x minus 5, but I need to multiply by 1 over 2 because 2 is that derivative. I'm doing a u sub, I'm just doing it quickly and easily in my head. Okay? If that confuses you, go off to the side and do a u sub on that piece. Minus, now we'll have a 1 here, and then now this time the derivative of the denominator is just a 1, so this is just natural log absolute value x minus 1. And we are going to evaluate that from 5 to infinity, but again, we cannot put infinity as a boundary. Make it your b, or make it some letter. Okay? Now, b is going to go in for x. This is just 1 here. Okay, b is going to go in for x, and then b is going to infinity. So essentially, I'm going to have ln of something going to infinity. That's infinity. Minus infinity. Well, infinity minus infinity is indeterminate. We don't know what that is. So we have to mess with this. An easy way to mess with logs is to combine them into a single log. So that's what I'm going to do. So we're going to have natural log of, this 2x minus 5 came from a positive log, so it goes on top. The x minus 1 came from a negative log, so it goes on the bottom. Now put b in for x and let b go to infinity. As b goes to infinity, the minus 5, the minus 1 don't matter, and I have 2. So ln of 2. So taking that limit yields ln of 2. Now we put 5 in for x. So we'll have minus natural log of 10 minus 5 over 5 minus 1. And that is a safe stop spot. I'm just going to safe stop right there. Okay? All right, part D. Determine whether this series converges or diverges. Well, we recognize this. This is the same as our function, right? And we want the series, the sum from 5 to infinity. And we want to know whether that converges or diverges. So now it's a series question. So, what do? Well, I see two really good ways to do this. The first way that I see to do it is that I know we just did the integral of this guy from 5 to infinity. 5 to infinity, everything's the same. We see that the integral converged, so I know the series is going to converge by integral test. So that's how I would do this problem. The other way to do it is by the limit comparison test, because I see that this will behave like 1 over n squared, which also converges. It's a converging p-series. So either way, pick one and go with it. I'm going to use the integral test. So I need to state my conditions of course, we always state on an FRQ, always state your conditions. So I'm going to say that f of x, which is what the function that we were given, is positive, continuous, and decreasing for x greater than or equal to 5. That's true. We have to state that if we're using the integral test. That's the conditions. Okay? The integral from 5 to infinity of f of x dx converges as shown in part B. Therefore, the sum from 5 to infinity of our expression with n's converges by integral test. Okay? That is one way to do this problem. The other way to do it would be, again, with that limit comparison test. So let me write what you would have to do if you chose to use a limit comparison test. First of all, the conditions for the limit for either of the comparison tests. Remember that the terms have to all be positive. So I'm going to write that. So first of all, the terms, this is greater than or equal to 0 for n greater than or equal to 5, and what I'm comparing it to is also greater than or equal to 0 for all n greater than or equal to 5. Okay? Both of those have to be true in order to use a comparison test. Now I'm going to set up the limit comparison test. So it's a limit comparison test has a limit, 3 over 2n squared minus 7n plus 5, and I'm dividing by 1 over n squared, which is the same thing as multiplying by n squared over 1. This is going to give me a 3n squared over this. When we take the limit, this part doesn't matter, and I'm left with 3 over 2. For limit comparison test, we were looking for finite and positive, and we got a finite and positive value for our limit. So our series does whatever the series does that we're comparing it to. So now I need to say that the series for 1 over n squared converges by p-series test. So the series that we're looking for converges by limit comparison test. And FRQ, if I have time, I will go ahead and fill in the little bells and whistles here. Okay, it doesn't take too long. So which one would you do? I don't know. They're both equally good. I thought to do the integral test just because I just did the integral. All right, next up. All right, next I would like to take a look at the problem from 2015. This was number 5, no calculator. Starts off kind of similar to our previous problem where they give us a function. It has a k in it. That's why I chose to do this with you here. I know k's can be a little bit disturbing to people. When in doubt, you treat k like a number, all right? In these problems, they're going to give you a value for k. So you can more than treat it like a number, you can make it a number, okay? They also in this problem gave us the derivative. We didn't have to go find it. They could have made us find it. They didn't make us do that. They just gave it to us. Part A. Let k equal 3, so f of x is equal to this. So they put 3 in for k. Write an equation for the line tangent to the graph of f at the point whose x-coordinate is 4. Well, we have been doing this all year long. I will be shocked if you guys can't do this one. So I know you can do this one. Equation of a line, we need a point and we need a slope. For the point, that's just going to be f at 4. So I'm putting 4 in for x right here. So we'll have 1 over 16 minus 12, 1/4. So the x-coordinate is 4, the y-coordinate is 1/4. For the slope, we're finding f prime at 4. So I am putting 4 in for x, and I'm putting 3 in for k. So this will be 3 minus 8 over 16 minus 3 times 4 squared. So that's a negative 5 over 4 squared. So the equation of the line would be y minus the y value is equal to our slope times x minus the x value. And I'll say stop there. This was worth 2 points. 1 point for the x. I'm sorry. Oh, I am still on the previous problem. This was worth 2 points. 1 point for the slope and 1 point for the tangent line equation. Oops. Alrighty. Part B. Let's let k equal 4 now. So now they told us what f is. Determine whether f has a relative min, max, or neither when x is 2. Since we only want when x is 2, I think I'm going to use the second derivative test here. So I'm going to begin by finding f prime at 2. F prime at 2. So here's my equation for f prime. I'm putting 4 in for k and 2 in for x. 2 in for x and 4 in for k. I want to make sure, I immediately saw that the numerator was 0. I wanted to make sure that the denominator was not 0 as well, and it's not. So this is 0. So now I'm going to go on and do the second derivative and see the sign of the second derivative. So the second derivative is the derivative of the first derivative. Now, the bad thing about this is I need to use the quotient rule. It's not going to be just terrible, though. So I start at the top, and I take the derivative with respect to x. The derivative with respect to x is negative 2 times the bottom, So the bottom will be x squared minus k, which is 4, x squared. That's the bottom. Minus, now the derivative of the bottom, a little chain rule here, derivative of the bottom, 2 times the inside, decrease the power by 1, times the derivative of the inside, 2x minus 4, since k is 4, all divided by the denominator squared. So we'll have x squared minus 4x to the 4th power. So that is the second derivative at x. Now I'm going to put 2 in for x, and I'm really only interested in the sign of this, right? And I see I did put a k here. This should be a 4 because k is 4. All right. 2 in for x. So I have a negative 2 times, this is going to be a 4 minus 8. 4 minus 8 is negative 4, but we're squaring it, so that's 16. Minus 2 times, okay, this is the same thing. So 4 minus 8, negative 4. And this is 4 minus 4. Well, that piece is 0. In the denominator, I have 4 minus 8 to the 4th, so that's going to be a positive number. 4 minus 8 is negative 4, but we're to the 4th power. So all I have is a negative over a positive, so this is going to be less than 0. So if we're concave down and have a slope of 0, think of that, concave down and a slope of 0. This means that we have f has a relative max when x equals 2, since f prime of 2 is 0 and f double prime of 2 is negative. Okay? Now, I did not have to write this since again, because I just showed it here. I don't have to say it twice. Part C. Find the value of k for which f has a critical point when x is negative 5. Another critical point problem for f. So I'm going to begin by saying what that means. So f has a critical point when f prime equals 0 or f prime is undefined. I never know if that's going to be worth a point or not, so I always say it. Okay? So f prime of x, I'm going to write this down again so I don't have to keep sliding it up. That's f prime of x. Okay? So f prime at negative 5 would be k plus 10 over 25 plus 5k squared. That's f prime at negative 5. All right? F prime at negative 5 equals 0 if k is negative 10. That's just the numerator is negative 10, right? F prime at negative 5 is undefined if k is a negative 5, right? However, when k is negative 5 and x is negative 5, when that's true, since we have the same denominator here, f is going to be undefined there. If f is undefined, we can't have a point. We don't have any point, much less a critical point. So this f at negative 5 is also undefined when k is negative 5. Okay? So that's not a critical point. So the only value of k that makes f have a critical point when x is negative 5 is k equals negative 10. So k equals negative 10 is the only value. That was worth just 1 point for the answer. Seems like a lot for 1 point. Part D. Oh, I didn't give you the points for Part B. For Part B, this was worth 2 points. 1 point for considers f prime at 2, which we did right at the beginning, and 1 point for our answer with justification. So we've had 5 points. That means down here this is going to be worth 4 points. Okay, let k equal 6. So now here's our f. Find the partial fraction decomposition for f. All right, that's something we can definitely do. We have this. I know I begin by factoring that bottom. And now I want to split the denominator. Split the denominator. That's a partial fraction decomposition. I need to find what goes here and what goes there. Let's call them A and B like we've always done. If I multiply both sides by the common denominator, I'm going to get 1 is equal to A times x minus 6 plus B times x. I can let x be anything I like. I'm going to begin by letting x be 6 so that my A term zeroes out and I just get the value of B. So B will be 1/6. Next I'm going to let x be 0 to let the B term zero out, and I'll get 1 is equal to negative 6a, so a is negative 1/6. So f of x is equal to negative 1/6 over x plus 1/6 over x minus 6, and that is the partial fraction decomposition. Okay? Quite honestly, we did not have to repeat this here because we have it all right there. Now we're going to use what we just did to find the integral. So the integral of f of x dx will be the integral of negative 1/6 over x plus 1/6 over x minus 6 dx. Negative 1/6 natural log absolute value x plus 1/6 natural log absolute value x minus 6 plus c. There is no reason to put these together. Just leave it like that and we're done. This was worth 4 points that year. 2 points for the partial fraction decomposition. And 2 points for the what they say general antiderivative. Don't know if they split that up, how they split it up, I don't know. I'm sure they split it up somehow or gave some kind of partial split this up, but I don't know what they did back then. Okay, so a couple of function analysis problems and then that one miscellaneous problem. I put them all into this topic. So your turn to try some.